having just spoken about continuity, it leads us to the point where we talk about a function being differentiable. Okay, so for a function to be differentiable, it means we can work out its gradient. All right, so first things first, for a function to be differentiable, it has to be continuous. Okay, so that kind of makes sense. If the function is not defined at a point, well, it can't have a gradient at that point. All right, now it's not enough for it just to be defined. The gradients either side of that point need to be coming to the same value. Okay, so for example, if I consider up here where the turning point is, if I get close to the graph from the left or close to the graph, or to that point, I should say, from the right, the gradients are both approaching zero. But let's consider this point, this one here. The gradient on the left-hand side is clearly greater than zero. The gradient on the left-hand side is clearly less than zero. So what happens there? Okay, that point there we call a cusp. And big statement there, the derivative does not exist there. Okay, so where we have those sort of sharp points, which is that one there and that one there, okay, the derivative doesn't exist. Here we have a zero derivative. It jumps automatically to a positive derivative at the point where they join. Which one is it? Okay, and it can't be both of them. So we call those points cusps, and our function can't be differentiated at that point. Now that becomes important when we talk about giving a domain for our gradient function, or the domain for the derivative. Okay, we can work out derivatives for this graph. We can work it out over that section there and that section there. We can do those individual sections, but where the graph isn't defined, so there, a cusp, not defined, there's no derivative at those points. Okay. Okay, so if we have a hybrid function, it's worth pointing out. Okay, we don't work around with the modulus function anymore, but we do hybrid functions. Remember, our hybrid function is when we have a set of different rules. It could be x squared where x is less than 0, 2x plus 1 for 0 is less than x, which is less than 4, and x cubed for x is greater than equal to 4. Yeah? So we have different sections, so we come up with different gradient rules for each section. All right? So let's have a look at those. For the following function, find the derivative and sketch the graph of f dash of x. So if that's my graph of f of x, f dash of x is equal to, we've got two rules. Derivative of that is 2x plus 2. And that's if x, now at the moment, we'll just put greater than or equal to 0. And for the next part, it's 2x plus 1, so it's 2 if x is less than or equal to 0. So what we need to do is check at the point x equal to 0. So if x is equal to 0, I get 2 there for the derivative. I get 2 there for the derivative. Because it's the same value, well then our derivative does exist at the point x equal to 0. Okay, so if I want to sketch my derivative graph, let's call this one green. If I want to sketch my derivative graph, it's a graph of 2x plus 2. So we've got an intercept at 2, it goes up there. So 2x plus 2 defined at that point, that's fine. Okay, and then we'll go with we'll keep it red. And it says at x less than 0, the derivative is equal to 2, which is there. Now notice the graph joins smoothly. My f dash of x graph joins smoothly at that point. Actually, it's not smoothly, it just joins. So it's because it's connected. So we can say f dash of x is continuous, can't we? And because it's continuous, that means it's defined at that point. All right. find the value of f dashed of -1. F dashed of -1 is equal to, well, which of these graphs? That one there is for f dashed of -1, so the gradient is equal to 2. But if I consider f dashed of 2, the top rule applies where x is greater than 0. So that's equal to 2 times 2's everywhere, 2 plus 2, which is equal to 6. All right. So I probably shouldn't have written that on green. So there's my derivative function. It's two separate sections. Because the derivative function is continuous and joins up at 0, the derivative is defined at 0. All right, what's example 17 talking about? Okay, so before we try and differentiate, let's have a think about whether the function's defined. So what is g of x? So don't forget we were trying to work out f of g of x. So g of 3 is equal to 3 plus 3 squared, which is equal to 12. And f of 12 is undefined. So we don't have to worry about trying to find the derivative because since the function is undefined at 3, there's no derivative. We spoke about that. So f of 3 is undefined. G of f, on the other hand, is going to be a bit different, isn't it? If you consider the function g of f, that's going to be equal to 3 plus the square root of 2 minus x squared all squared, which is just 3 plus 2 minus x squared, 5 minus x squared. Now the domain of g is R, so it's always going to be defined as a composite function. So let's work out g of f dashed, which is simply equal to -2x. So g of f dashed of 3 is -6. All done.